We are looking at a paper today titled Think Deep, Not Just Long. It is by Weilin Chen and a team from the University of Virginia and Google. And the headline here is a direct challenge to the current meta of chain of thought reasoning.
It really is. The core problem they address is this assumption that longer reasoning chains automatically equal better answers. This paper proves that token count is actually an incredibly unreliable proxy for reasoning quality. In fact, they found it often signals overthinking or spiraling.
Right. So instead, they introduced the deep thinking ratio, or DTR. And this measures how hard a model is thinking by tracking how its internal token predictions evolve layer by layer. If a token's prediction fluctuates deep into the network before stabilizing, it is considered a deep thinking token.
And the empirical results are just incredibly strong. DTR correlates with accuracy at around 0.828 on hard math benchmarks like AIM, significantly outperforming any length-based metrics.
They also propose a test time scaling strategy called Think at N. By measuring the DTR of just the first 50 tokens of a response, they can predict if the reasoning is going to be good. This lets them match or beat standard majority voting performance while slashing inference costs by roughly 50%.
So essentially, we can predict correctness during generation and stop wasting compute on yapping.
Exactly. Welcome to AI Paper Podcast. Let's really break this down.
Yeah, let's get into it.
So we have covered the headline. But to understand why this matters right now, we have to look at where we are with reasoning models in the industry. We're totally in the era of inference time scaling. You look at O1, you look at DeepSeek R1.
The strategy is just let it think.
Let it think, exactly. And let it think in an LLM context literally means let it generate tokens. The intuition is kind of biological, right? If I give you a complex physics problem, you need time to work it out. In a transformer, time is sequence length.
Right, so the industry heuristic has basically been more tokens equals more cognitive work.
Right. But you've got some recent literature popping up that suggests this relationship isn't linear at all.
No, it's actually an inverted U relationship. Initially, yes, showing your work helps the model. But past a certain point, more tokens usually mean the model is just confused. It starts hallucinating, it creates error cascades, or it just loops indefinitely.
We have also models that write 5,000 words just to ultimately get the wrong answer.
Exactly, the overthinking problem. So the goal of this paper was to find a metric that separates effective reasoning from just verbose text generation. And they really wanted to do it without needing ground truth labels, so you can use it on the fly during generation.
Which brings us to the core mechanism. They needed to open the black box. How do they actually measure thinking inside the layers?
They utilize a technique that's often called the logit lens, or unembedding projection. It is based on some older interpretability work from back around 2020.
Walk us through the technical setup of that. How does it work?
So normally in a transformer, you have a hidden state at every layer. Let's say you have an 80-layer model. We usually only project the final layer, layer 80, into the vocabulary to figure out what the next word is.
Right, the final output.
But technically, you can take the hidden state at layer 10 or layer 40 and project it using that exact same final unembedding matrix.
So you are essentially asking the model, hey, if you were forced to stop thinking right now at layer 10, what would your next word be?
Precisely. You get a probability distribution over the entire vocabulary at every single layer.
Yeah.
This allows you to essentially watch the model make up its mind as the signal propagates up through the network.
And this is where they found a massive distinction between what they call easy tokens and hard tokens.
Yes. They analyze the stabilization patterns of these predictions. Take a functional word like the or is or standard formatting tokens like boxed. They found these stabilize incredibly early.
How early are we talking?
By layer 5 or 10, the distribution at that early layer looks almost identical to the final layer. The model knows it's going to say the, and it effectively stops processing that token.
It's just propagating the signal upward at that point. It's like muscle memory.
Exactly. But hard tokens are totally different. We are talking about numbers in a complex calculation, logical operators, or the specific answer option in a multiple choice question. These undergo what the authors call sustained revision.
Sustained revision. I like that term.
Yeah. At layer 10, the model might predict a 5. At layer 30, it shifts to a 7. At layer 60, it might oscillate back to a 5. It doesn't actually stabilize until the very deep layers. That fluctuation indicates the model is actively using those layers to transform the information.
And they quantify this fluctuation using a metric called Jensen-Shannon divergence, or JSD.
Correct. JSD measures the distance between two probability distributions. They compare the distribution at a given intermediate layer with the final distribution at the very last layer.
Why did they choose JSD specifically? Why not cosine similarity or KL divergence? Those are pretty standard.
They actually ran a full comparison. Cosine similarity was too unstable, it was just noisy. KL divergence is the standard for distributions, sure, but it's asymmetric and it completely blows up if probabilities get near zero.
Which happens constantly in LLMs.
All the time. JSD is symmetric and it is bounded between 0 and 1. It just gave them a much cleaner, more reliable signal for distance.
Okay, so they have the metric, and then they define a settling depth.
Right. The settling depth is basically the first layer where the JSD drops below a certain threshold, defaulting to 0.5, and stays there.
And from that, they define a deep thinking regime.
They set a depth parameter, usually 0.85. Basically, if a token stabilizes after 85% of the layers, so in a 40-layer model, if it is still fluctuating at layer 34, it counts as a deep thinking token.
And the deep thinking ratio, the DTR, is just the ratio of these specific deep thinking tokens to the total sequence length.
Exactly. High DTR means a significant portion of the response required deep layer-wise processing. Low DTR means the model was mostly coasting on surface-level statistics.
Theoretically, this is incredibly sound. Harder concepts require more layers. But does it actually predict accuracy? Because if I am thinking really hard about the wrong answer, that doesn't actually help me solve the problem.
That is the crucial question. And they tested this on a very rigorous suite of benchmarks. AEM 2024 and 2025, HMMT 2025, so serious competitive math, and GPQA Diamond, which is graduate-level science.
And they used multiple model families to make sure it generalizes.
They did. They used GPT-OSS 20 billion and 120 billion variants, DeepSeek R170 billion, and Qwen3 30 billion thinking model.
And the correlation with accuracy.
It was startlingly high. The average correlation coefficient across these tasks was 0.828.
Wow.
Yeah. In the noisy world of LLM evaluations, anything above 0.5 is considered good. 0.8 is spectacular.
But here is the part that I think is going to surprise a lot of engineers listening. They compared this DTR metric to raw token count.
Yes. The length fallacy. This was honestly the most striking chart in the whole paper.
Yeah.
They plotted accuracy against token count, and the correlation was negative, average negative 0.594.
Negative 0.6. That is statistically massive. So literally, the longer the model talked, the more likely it was to be completely wrong.
On average, yes, for these specific hard tasks. The authors suggest that excessive length is a proxy for the model being totally lost. It is rederiving coordinates, it's going in circles, it's spiraling.
It's generating tokens, but it's not doing effective compute.
Exactly. You are increasing the surface area for errors without actually increasing the depth of thought.
That perfectly explains why simply prompting a model to write a longer chain of thought doesn't always yield better results. You might just be forcing it to hallucinate filler text.
Right. They also compared DTR to standard confidence metrics like log probabilities or self-certainty prompting.
How did those stack up?
They work okay. They have positive correlations, but they are very inconsistent across different models. One model might be well-calibrated, another might be totally overconfident. DTR was by far the most stable predictor across every single architecture they tested.
There is a visualization in the paper, figure 2, that I think really lands this concept for me. It is a heat map of the token representing the number 13.
Oh, I love that figure. So the model is solving a complex math problem. The final answer is 13. In the early layers, like layers 1 through 10, the probability for 13 is basically 0. The model is considering all sorts of numbers.
Just feeling at the math space.
Yeah. Then in the middle layers, 13 starts to creep into the top predictions, but it is heavily fighting with other numbers. It's oscillating. It is only in the final few layers that 13 actually locks in as the dominant prediction.
And they contrast this heat map with the token boxed, which is just part of the standard LaTeX output format.
Right. Box stabilizes almost immediately. Layer 2. The model knows the format long before it actually knows the math answer. That visual proof really validates that DTR is measuring cognitive load, not just syntax generation.
Now, for the ML engineers out there who might want to implement this today, how sensitive is this metric to the hyperparameters? If I tweak that threshold, does the whole thing break?
They did a full sensitivity sweep. They looked at the threshold and the depth fraction. They found that the threshold of 0.5 is really the sweet spot. If you make it too strict, like 0.25, you filter out way too much signal. If you make it too loose, you just capture noise.
And what about the depth fraction?
That is where you define what deep actually means. whether it is the last 15% or the last 5% of layers. Varying that shifts the absolute DTR values, obviously, but it entirely preserves the positive slope.
So the correlation with accuracy remains robust, even if you change the definition of deep slightly.
Correct. The phenomenon of late settling for complex tokens appears to be a fundamental property of transformer inference. It's not just a statistical artifact of specific settings.
Okay, let's talk utility. We have a metric that works. How do we turn this into actual cost savings? This is where the think at n method comes in.
This is the killer app of the paper. So currently, for hard reasoning tasks, we use best of n or self-consistency. You generate n solutions, say 48 of them, and you take a majority vote.
Which is incredibly expensive. You are paying for 48 full chains of thought.
Exactly. And as we know from the negative correlation we just talked about, half of those might be extremely long, incorrect ramblings. So you are paying extra compute for the failures.
So how does think at n actually fix this pipeline?
The authors discovered a really useful property. You don't need the full sequence to estimate the final DTR. You can estimate it highly accurately from just a prefix.
How short of a prefix are we talking?
They found that calculating DTR on just the first 50 tokens is highly predictive of the DTR for the entire sequence.
50 tokens is nothing. That is barely the opening sentence of a chain of thought.
It is tiny. But it seems the model reveals its cognitive stance almost immediately. If it starts off with deep, unstable tokens in the first 50, it's likely engaging in effective reasoning. If it starts off shallow and stable, it is likely just going to hallucinate and yap.
So the algorithm is basically you start generating 48 samples, you stop every single one at 50 tokens. Calculate the DTR, pick the top 50%, finish generating only those, and then vote.
And just like that, you have cut your inference token cost by roughly 50%.
And what happens to the performance?
It matches or beats standard consensus. On AME 2025, standard consensus with 48 samples achieved 92.7% accuracy. Think at N achieved 94.7%.
Wait, it actually went up.
It went up because you are actively filtering out the confident failures and the spiraling answers before they even have a chance to pollute the voting pool. It's literally addition by subtraction.
I want to ground this in a specific example they provide in the paper. They discuss a geometry problem from AIM 2025 about tangent circles. It is really a tale of two models.
This case study perfectly illustrates the difference between token length and real reasoning. The problem is complex geometry. Sample A from the model fails completely, but it generates 27,724 tokens.
27,000 tokens. That is a literal novella for one math problem.
It is absurd. The model kept getting lost. It set up the coordinate system, doubted itself, re-derived the whole thing, tried to factor a quadratic, got stuck, assumed the rectangle was rotated. It was just spiraling out of control.
And what was the DTR for that novella?
13.9%. Very low. Even though it was generating a mountain of text, the internal layers were stabilizing early. It wasn't actually thinking hard. It was just reciting math concepts.
And sample B?
Sample B was the success. It generated 3,725 tokens, about 1/7 the length. It was concise, it established the coordinates, solved the system, and confidently output the answer.
And the DTR for the concise answer?
19.0%, significantly higher.
This completely flips the show your work heuristic on its head. The shorter, correct answer had the higher deep thinking ratio.
It challenges our entire definition of thinking in AI right now. We tend to equate thinking with the output of text. But this suggests that the hardest thinking happens when the model is manipulating abstract representations internally before it commits to a token.
The conciseness of the correct answer was a result of clarity, and that clarity came from deep layer-wise processing.
Exactly. The hard thinking wasn't in the length, it was in the depth.
So wrapping up here, we have a new metric, DTR. We have a new scaling method, think at n. And we have a thoroughly debunked fallacy regarding token length. What does this mean for the future of model training?
I think the absolute biggest implication is for reinforcement learning. Right now, when we train reasoning models using RLHF or RLAIF, we often implicitly reward length. If a model explains more or looks like it is trying harder, humans often rate it higher.
But we could just reward DTR directly during training.
Exactly. Imagine a reward function that explicitly penalizes early layer stabilization for complex tokens. You could train a model to maximize deep thinking density.
You might end up with models that are far more concise, but where every single token carries significantly more cognitive load.
It redefines what we mean by compute. We always say inference time compute, and we usually mean generate more tokens. But this suggests true compute is depth-wise.
The authors actually state this pretty boldly in their conclusion. We need to shift from think long to think deep.
It implies we might be wasting massive amounts of GPU time generating fluffy chains of thought, when we should really be figuring out how to force the model to utilize its full depth on fewer tokens.
I want to leave you with a thought here, building on this. If we can measure how hard a token is thinking at the intermediate layers, could we dynamically route compute per token during inference?
Oh, like early exiting.
Yes. If a functional token stabilizes at layer 10, why are we running it through layers 11 to 80? What if the transformer architecture itself could dynamically halt computation on a per-token basis depending on the JSD?
That is the ultimate efficiency dream. You could speed up inference massively without losing any quality on the actual reasoning steps. We wouldn't even need human-defined thresholds.
The potential here for optimization, both in training and inference, is just massive. It really feels like we have been using a blunt instrument with token counting, and we just got handed a scalpel.
That is a perfect analogy.
For the researchers and ML engineers listening, the paper is think deep, not just long. It is definitely worth a full read, especially for the specific implementation details of the unembedding projection.
And really check out the think at N algorithm. It is surprisingly straightforward to implement if you already have access to your model's logisets.
That is all we have for this deep dive into the latest research. Keep an eye on those layer-wise distributions.
Absolutely.
Thanks for listening to AI Paper Podcasts. We will see you on the next one.